spring 1940, Cincinnati, Ohio. The factory floor hummed with a rhythm that European machine tool experts insisted was impossible. 35-year-old Fred Geier watched precision milling machines roll off his assembly line, each one built to thousandths of an inch accuracy, while stopwatches confirmed what traditional craftsmen refused to believe. 17 minutes per machine. European master tool makers had spent centuries perfecting their craft, declaring that precision machinery required months of hand-fitting by skilled artisans, each component individually crafted, each machine a unique creation, no shortcuts, no assembly lines, no mass production methods that could possibly achieve the accuracy needed for wartime manufacturing. But here in Cincinnati, identical machine tools moved down the line with automotive precision, assembled by workers trained in weeks rather than decades. While Hitler's war planners counted on traditional manufacturing bottlenecks to limit Allied production, Geier was proving that American ingenuity could build precision faster than European tradition ever imagined. The most remarkable part? Today's computer-controlled machines still take hours to set up for the same work Geier's assembly line workers completed in minutes. How did a 1940s factory solve a problem that modern technology still struggles with? The telegram from the British Purchasing Commission arrived at Cincinnati Milling Machine Company on a gray March morning in 1940, its urgent language cutting through the routine correspondence that typically crossed Frederick Geier's desk. $16.5 million worth of precision machine tools, needed immediately. The British weren't asking, they were pleading. Their own manufacturing capacity, centuries in the making, lay vulnerable to German bombers that crossed the English Channel nightly, reducing entire industrial districts to rubble and twisted steel. But the telegram represented more than British desperation. It revealed the mathematical impossibility that would define the next 2 years of American industrial mobilization. European machine tool manufacturers, operating from workshops in Switzerland, Germany, and England, had spent generations perfecting their craft through methods that seemed immutable. Master toolmakers trained apprentices for 7 years before trusting them with precision work. Each milling machine emerged from months of careful assembly, with components hand-fitted to tolerances measured in thousandths of an inch. The Swiss could deliver perhaps 12 precision machines per year from a single workshop. The Germans managed similar numbers. Even Britain's most productive facilities rarely exceeded 20 machines annually per master craftsman. Heinrich Zimmermann, representing a consortium of European machine tool manufacturers, had arrived in Cincinnati just weeks before the British telegram, carrying with him the accumulated wisdom of continental manufacturing traditions. Walking through Geier's existing production facility, the 60-year-old German engineer observed the American methods with barely concealed disdain. American workers, he noted in his careful English, lacked the fundamental understanding of precision work that came only through decade-long apprenticeships. They operated machines without truly comprehending the metallurgical principles that governed cutting tool performance. Most damaging to any hope of rapid expansion, they showed little appreciation for the patient hand-fitting that distinguished quality European machinery from crude American approximations. Each spindle bearing, Zimmermann explained to a gathering of American machine tool executives, must be individually matched to its housing through careful filing and adjustment. The thermal expansion characteristics of the steel, the precise alignment of rotating assemblies, the microscopic irregularities that appear in even the finest castings. These require the trained eye and experienced hand of a master craftsman. Your assembly line methods might suffice for automobiles, where tolerances can be measured in hundredths of an inch, but precision machine tools demand accuracy to the thousandth. This cannot be rushed. Frederick Geier absorbed these pronouncements while calculating numbers that transformed confidence into cold fear. At 35, he commanded America's largest machine tool company, employing nearly 4,000 workers in facilities that sprawled across 150 acres of Cincinnati's industrial district. The company his father had built through methodical expansion and technological innovation now faced a mathematical challenge that defied every precedent in manufacturing history. By 1941, America would need to produce machine tools at levels that exceeded the combined output of all European manufacturers. Conservative estimates suggested 30,000 precision machines would be required to arm democracy's industrial mobilization. Using traditional methods, Cincinnati Milling could deliver perhaps one machine tool per week from each master craftsman station. With 50 experienced toolmakers on staff, the company might manage 2,600 machines per year, assuming perfect efficiency and no breakdowns, sick days, or material shortages. But America needed production rates that staggered comprehension. To meet projected demand, the nation's machine tool industry would have to deliver one completed machine every 17 minutes, 8 hours a day, 7 days a week, for 2 years running. The technical requirements made the mathematical impossibility even more daunting. A single air-cooled aircraft engine demanded 17,000 individual components, with cylinder barrels alone requiring 88 separate machine tools to achieve the precise dimensions that would allow Wright Cyclone engines to power B-17 flying. Fortresses. Tank armor required specialized boring mills capable of drilling gun ports with accuracy measured in fractions of degrees. Naval construction demanded massive horizontal mills that could machine ship components weighing several tons while maintaining surface finishes smooth enough for critical pressure vessels. Each of these machines represented months of specialized work under European methods. The spindle assemblies required hand-selected bearings, individually adjusted for minimum runout. The precision lead screws that controlled table movement needed careful calibration to eliminate backlash that would compromise cutting accuracy. Most complex of all, the gear trains that synchronized cutting speeds with feed rates demanded individual timing adjustments that could take skilled mechanics days to perfect. Geier studied the production schedules that his engineering staff had prepared, cross-referencing British requirements with preliminary American mobilization estimates. The numbers revealed a manufacturing challenge that transcended normal business calculations. Even if Cincinnati Milling doubled its workforce, tripled its factory space, and operated around the clock, traditional craftsmanship methods would deliver perhaps 10% of the machine tools that democracy needed to survive. European manufacturers, operating from their scattered workshops, might contribute another 5% if German bombers allowed uninterrupted production. The gap between need and capacity yawned like an industrial abyss. Somewhere between the British telegram's urgent plea and Heinrich Zimmermann's careful explanation of why rapid expansion was impossible, Fred Geier began to understand that conventional wisdom would lose the war before it began. American industry could either revolutionize precision manufacturing or watch democracy surrender to totalitarian efficiency. Traditional methods, perfected over centuries, had become the enemy of survival itself. The inspiration struck Frederick Geier during an April visit to Ford's River Rouge plant, where he watched identical V8 engine blocks move down assembly lines with mechanical precision that European craftsmen would have dismissed as impossible. Each engine emerged from the line fully assembled, tested, and ready for installation, built by workers who specialized in single operations rather than mastering entire assemblies. The automotive industry had already solved the fundamental challenge that paralyzed machine tool manufacturing: how to achieve consistent quality through systematic processes rather than individual craftsmanship. Standing on the River Rouge observation deck, Geier began sketching connections between automotive assembly and precision machinery that his engineering background made visible. Machine tools, despite their complexity, consisted of standardized subsystems that could be pre-manufactured and tested independently. Spindle heads, table assemblies, drive, mechanisms, and control systems, each component could be built to precise specifications in specialized production cells, then combined during final assembly according to customer requirements. The key insight was modularization. Instead of building each machine as a unique creation, Cincinnati Milling could manufacture component libraries that assembled into countless configurations. By late April, Geier had mobilized his engineering staff to redesign the company's entire product line around modular principles. Chief Engineer Robert Manning led teams that analyzed every Cincinnati machine tool, breaking complex assemblies into standardized modules that could be manufactured independently. The horizontal milling machine, traditionally built as an integrated unit requiring months of hand fitting, became a collection of precision modules: the base casting, spindle head assembly, table and weigh system, drivetrain, and control mechanisms. Each module would be manufactured to exact specifications, tested separately, then joined through precision-machined interfaces that eliminated hand-fitting entirely. The breakthrough came when Manning's team realized that modular design actually improved precision rather than compromising it. Traditional hand-fitting methods introduced human variables that affected final accuracy. Individual craftsmen had different techniques, different standards, different interpretations of acceptable tolerance. Modular assembly based on precision-machined mating surfaces and standardized connection protocols eliminated human inconsistency. Each spindle head would mate with each base, casting through identical mounting surfaces machined to tolerances of 5/10,000ths of an inch. Quality became systematic rather than personal. The new foundry that Cincinnati Milling had completed in December 1939 provided the manufacturing foundation for modular production. Instead of casting complete machine bases that required months of machining, the foundry began producing standardized component castings, spindle head housings, table bases, column sections, and drive assemblies. Each casting incorporated precision-machined mounting surfaces that would accept standard modules without adjustment. The foundry operated around the clock, building inventory of precast components that eliminated the traditional bottleneck of custom casting for each machine order. Manning established component production cells throughout the Cincinnati facility, each specializing in manufacturing specific modules to exact specifications. Cell 7 produced spindle head assemblies, incorporating precision bearings from Swedish suppliers, American-made cutting tool holders, and lubrication systems tested to military specifications. Each spindle head underwent individual testing on specialized fixtures that verified runout accuracy, vibration characteristics, and thermal stability before approval for final assembly. Cell 12 manufactured table assemblies, combining precision ground weighs with lead screws accurate to 1/10,000th of an inch per foot of travel. The drive system cell presented the most complex challenge, requiring gear trains that synchronize cutting speeds with table feeds across wide ranges of operational requirements. Manning's team developed modular gearboxes that could be reconfigured for different applications by changing gear sets rather than rebuilding entire transmissions. A Navy contract for ship hull drilling required high torque at low speeds. An Army specification for tank armor work demanded rapid material removal with precise depth control. The modular drive system accommodated both requirements using identical base assemblies with application-specific gear modules. By August 1940, the first complete machines began emerging from Cincinnati's revolutionary assembly line. Instead of individual craftsmen building machines from raw castings, teams of specialized workers assembled pre-manufactured modules according to engineering specifications. The process began with base casting selection, continued through module mounting using precision-machined interfaces, and concluded with integrated testing that verified complete machine performance. Workers trained for weeks rather than years, learning specific assembly procedures that eliminated guesswork and standardized quality. The assembly line itself incorporated lessons from automotive production while addressing the unique requirements of precision machinery. Unlike automobile assembly, where speed dominated all considerations, machine tool assembly balanced production rate with accuracy requirements that demanded careful verification at each station. Station 1 positioned the base casting and verified mounting surface conditions. Station 2 installed the spindle head assembly using torque specifications that ensured proper bearing preload without introducing stress concentrations. Station 3 mounted the table assembly, checking weigh alignment and lead screw backlash before final tightening. Most revolutionary was the testing protocol that concluded each assembly. Every machine underwent complete operational testing before leaving the line, including spindle runout verification, table positioning accuracy, and cutting performance evaluation using standardized test cuts. Machines that failed testing returned to specific stations for correction rather than requiring complete rebuilding. The modular design meant that defective components could be replaced without affecting other systems, eliminating the cascading problems that plagued traditional assembly methods. The first production statistics validated Geier's revolutionary approach. Machines that previously required 12 weeks of craftsman assembly now completed the production line in 17 minutes of assembly time, plus component manufacturing that occurred independently of final assembly scheduling. Quality: measurements showed improved consistency compared to hand-built machines, with spindle run-out accuracies averaging better than traditional methods, and table positioning repeatability exceeding European standards. Most importantly, production capacity increased dramatically without requiring master craftsmen whose training took years to complete. By early 1941, Cincinnati Milling Machine Company had transformed into a production juggernaut that defied every prediction made by European manufacturing experts. The assembly line that Heinrich Zimmermann had declared impossible now delivered completed machine tools at a rate that staggered traditional industry calculations. Production had escalated to 7 times 1939 levels, with machines rolling off the line every 17 minutes during peak operational periods. The mathematical impossibility of the previous year had become routine industrial reality. The numbers validated Fred Geier's revolutionary approach in ways that transcended theoretical debates about manufacturing philosophy. Where European workshops delivered 12 to 20 precision machines annually per master craftsman, Cincinnati's modular assembly system produced over 4,000 completed units by December 1941. Each machine met or exceeded traditional quality standards while requiring assembly times measured in minutes rather than months. The production rate nearly doubled America's total machine tool output, transforming the strategic balance between democratic and totalitarian industrial capacity. The human component of this industrial revolution proved as remarkable as the mechanical innovations. Cincinnati Milling's formal 3-stage training program had evolved into a systematic method for converting ordinary workers into precision manufacturing specialists within weeks rather than years. Stage 1 introduced workers to modular component recognition and handling procedures, teaching them to identify spindle heads, table assemblies, and drive systems by visual inspection. Stage 2 covered precision mounting techniques, including torque specifications, alignment procedures, and quality verification methods that ensured consistent assembly results. Stage 3 integrated workers into the flowing production line, where they mastered specific station responsibilities while maintaining awareness of upstream and downstream operations. Rose McCarthy exemplified the transformation of American industrial workers during this period. Arriving from a Depression-era farming family that had lost their land to bank foreclosure, she entered Cincinnati's training program with no manufacturing experience beyond basic mechanical aptitude. Within 3 weeks, she had mastered the precision spindle head mounting procedures at Station 2, achieving assembly times that matched experienced workers while maintaining quality standards that exceeded traditional hand-fitting methods. Her spatial intelligence, previously applied to farm equipment repair, proved invaluable for visualizing how modular components would function together before physical assembly. The production line itself had become a choreographed industrial ballet, with workers moving between stations in synchronized patterns that maximized efficiency while maintaining the precision requirements of military specifications. Base castings entered the line at predetermined intervals, traveling on powered conveyors that positioned them accurately at each assembly station. Workers had exactly 12 minutes to complete their assigned operations before the next casting arrived, creating production rhythm that eliminated both rushing and idle time. The 17-minute total assembly time included 4 minutes of integrated testing that verified complete machine performance before final approval. Military contracts drove production complexity beyond simple quantity requirements. Navy specifications for ship hull drilling demanded machine tools capable of boring holes through 8-inch steel plate while maintaining dimensional accuracy sufficient for watertight fitting. The modular system responded by combining heavy-duty spindle heads with extended table assemblies and high-torque drive systems, creating specialized configurations without requiring custom engineering for each contract. Army tank production contracts specified machine tools for armor plate work that required rapid material removal combined with precise depth control for welded joint preparation. Again, modular assembly provided solutions through component selection rather than machine redesign. The confidence crisis emerged precisely when success seemed most assured. Traditional machine tool manufacturers, both European and American, began challenging the quality of mass-produced precision machinery through industry publications and direct communication with military procurement officers. Master craftsmen argued that modular assembly eliminated the individual attention that complex machinery required, creating machines that appeared precise during initial testing but would fail under sustained combat production demands. Swiss manufacturers suggested that American assembly line methods produced industrial toys that lacked the robust reliability of hand-built European machines. Heinrich Zimmermann, now representing a coalition of traditional manufacturers, returned to Cincinnati in late 1941 with detailed technical criticisms of modular machine tools. His inspection team identified potential weakness points at component connection interfaces, arguing that precision-machined mounting surfaces could not replicate the custom fitting that master craftsmen achieved through careful handwork. Thermal expansion under heavy cutting loads, they claimed, would reveal gaps in American manufacturing philosophy that European methods had eliminated through centuries of refinement. Most damaging to Cincinnati's reputation, they suggested that modular machines would require frequent recalibration and component replacement that would prove more expensive than the initial cost savings. William Crawford, Cincinnati's most experienced master machinist, found himself torn between pride in American innovation and concern about abandoning proven methods. His 30 years of precision work had trained him to detect minute mechanical problems through sound and vibration that automated testing might miss. Walking the assembly line, he noted that younger workers assembled modules according to specifications without developing the intuitive understanding of mechanical systems that distinguished master craftsmen from mere assemblers. The systematic precision impressed him, but he worried whether standardized procedures could anticipate the infinite variations that occurred in real manufacturing environments. The production statistics that had initially validated Geier's approach now became ammunition for critics who questioned whether quantity could sustain quality under combat conditions. The 17-minute assembly time that seemed miraculous in peacetime might prove inadequate when machines faced the sustained loads of 24-hour wartime production schedules. European manufacturers had tested their machines through decades of operation, while American modular designs had operated for months at most. The ultimate test would come when democracy's survival depended on industrial machinery performing flawlessly under conditions that no peacetime manufacturer had ever experienced. The radio crackled to life at 7:55 a.m. Hawaiian time on December 7, 1941, carrying news that transformed Fred Geier's manufacturing challenge from urgent to apocalyptic. Pearl Harbor lay in ruins. American battleships burned in the Pacific, while Japanese aircraft returned to their carriers, having demonstrated that modern warfare moved at speeds that made traditional industrial mobilization obsolete. Within hours, President Roosevelt would address Congress with demands that staggered comprehension. 50,000 aircraft annually, supported by industrial capacity that America had never imagined possible. The mathematics of survival now dwarfed every previous calculation. 50,000 aircraft meant 50,000 engines, each requiring 17,000 precision machine components. The Wright Cyclone engines that powered B-17 flying fortresses alone demanded 47 different machine tools for cylinder barrel production, with each tool operating continuously to meet projected requirements. Liberty ship construction called for massive horizontal mills capable of machining propeller shafts 30 feet long to tolerances measured in thousandths of an inch. Tank production required specialized boring mills that could machine gun tubes while maintaining internal dimensions accurate enough for artillery shells traveling at supersonic velocities. Colonel James Morrison arrived at Cincinnati Milling on December 15th with the systematic skepticism of a career military engineer who had witnessed too many civilian contractors promise capabilities they could not deliver. His inspection team carried testing protocols developed at Aberdeen Proving Ground specifically to evaluate whether American mass production could achieve the precision that combat conditions demanded. Unlike peacetime manufacturing, where machines operated intermittently with regular maintenance intervals, wartime production required continuous operation under maximum loads that revealed weaknesses invisible during normal testing. Morrison's team established testing procedures that pushed Cincinnati's modular machines beyond any conditions the assembly line had anticipated. Spindle heads designed for intermittent operation ran continuously for 72 hours while cutting hardened steel at maximum feed rates. Table assemblies underwent positioning tests that simulated 6 months of combat production scheduling, compressed into single weeks of operation. Drive systems faced load testing that replicated the stress of machining tank armor under emergency production quotas that eliminated scheduled maintenance periods. The first failures appeared within days of Morrison's testing protocol implementation. A spindle head assembly that had passed all standard quality checks developed bearing wear that exceeded acceptable limits after 48 hours of continuous operation. The precision machined mounting interface between the spindle head and base casting showed microscopic movement under sustained cutting loads, creating dimensional variations that accumulated over extended production runs. Most concerning to military inspectors, the modular connection points that enabled rapid assembly also created potential failure modes that traditional hand-fitted machines avoided through individual customization. Heinrich Zimmermann observed the testing failures with the satisfaction of a master craftsman whose warnings had proven prophetic. The German engineer documented each malfunction with methodical precision, noting that American modular design had sacrificed the individual adjustment that allowed European machines to accommodate the inevitable variations in materials, cutting conditions, and operational loads. Traditional hand-fitting methods, dismissed as inefficient by American mass production advocates, actually created machinery that adapted to real-world conditions through the subtle variations that master craftsmen introduced during assembly. William Crawford found vindication in the testing failures that confirmed his deepest concerns about abandoning proven manufacturing methods. Walking through the testing area where Cincinnati's machines struggled under Morrison's protocols, he observed mechanical problems that his trained ear could have detected during assembly if workers had possessed the experience to recognize subtle indicators of impending failure. The systematic precision of modular assembly had eliminated the individual craftsman's ability to adjust components based on the unique characteristics that every machine exhibited during initial operation. The technical problems extended beyond individual component failures to reveal systematic weaknesses in the modular approach that threatened the entire concept of mass-produced precision machinery. The standardized mounting surfaces that enabled rapid assembly also created uniform stress concentrations that appeared simultaneously across multiple machines, suggesting design flaws rather than manufacturing defects. Traditional hand-fitting methods distributed stresses through subtle variations that prevented cascading failures, while modular assembly concentrated identical loads at identical connection points throughout the production line. Fred Geier faced the collapse of everything he had built during the previous 18 months of revolutionary development. Military inspectors prepared reports that would recommend against Cincinnati Milling for major wartime contracts, arguing that the company's modular machines lacked the reliability that combat production demanded. European manufacturers, monitoring American testing failures through industry intelligence networks, prepared to supply precision machinery that their traditional methods could guarantee through proven performance under decades of operational experience. The engineering team that had created the modular revolution now worked desperately to identify solutions that would salvage their approach before military procurement officers canceled existing contracts and returned to European suppliers whose hand-built machines had never failed similar testing. Robert Manning's staff analyzed failure modes with the intensity of combat engineers, seeking modifications that could preserve the production advantages of modular assembly, while achieving the reliability that traditional methods provided through individual craftsmanship. As 1941 ended with American entry into global war, the fundamental question remained unresolved. Could American industrial ingenuity create precision machinery reliable enough for total war? Or would the assembly line approach collapse under conditions that European craftsmen understood through centuries of experience? The mathematics of survival demanded an answer that would determine whether democracy possessed the industrial foundation necessary to defeat totalitarian efficiency. Traditional wisdom had never seemed more validated, while revolutionary innovation faced its ultimate test under conditions where failure meant surrender to forces that threatened civilization itself. The moment of truth approached with the mathematical certainty of an engineering calculation carrying consequences that extended far beyond manufacturing philosophy to the fundamental question of whether American methods could sustain the industrial mobilization that freedom required to survive. The breakthrough emerged from failure analysis that revealed solutions rather than fundamental flaws in modular design. Robert Manning's engineering team discovered that the stress concentrations at connection points could be eliminated through redesigned mounting interfaces that distributed loads across larger surface areas. Instead of abandoning the modular approach, Cincinnati Milling implemented improved connection protocols that incorporated backup systems and stress distribution modifications based on the precise failure modes that Colonel Morrison's testing had identified. The foundry operations provided crucial rapid iteration capability, allowing engineers to test new mounting designs within days rather than months of identifying problems. By February 1942, the revised modular machines began passing military stress tests that had defeated earlier designs. The improved spindle head connections incorporated wider bearing seats and distributed mounting bolts that eliminated the concentrated loads responsible for previous failures. Table assemblies received redesigned weigh systems with multiple contact surfaces that provided redundancy against wear-related positioning errors. Most significantly, the drive systems incorporated backup gear trains that automatically engaged when primary systems showed signs of excessive wear, ensuring continuous operation under combat production conditions. The production miracle that followed validated every aspect of Fred Geier's revolutionary vision while exceeding even optimistic projections. American machine tool production reached 307,000 new units in 1942, representing a tenfold increase over 1938 levels and surpassing the combined peacetime output of all European manufacturers. Cincinnati Milling's 17-minute assembly rate became the backbone of arsenal democracy, enabling aircraft factories to increase production from 2,000 units annually to 50,000, shipyards to launch Liberty vessels at rates that outpaced German submarine construction, and tank plants to deliver armor that overwhelmed Axis manufacturing capacity through sheer volume. The systematic advantages of modular design became evident as American industry scaled to wartime requirements that traditional manufacturing methods could never have accommodated. European workshops, even operating at maximum capacity without bombing interruptions, could have delivered perhaps 5,000 precision machine tools annually. American modular production provided the 60,000 specialized machines required for aircraft engine manufacturing alone, while simultaneously supplying the 30,000 additional units needed for shipbuilding and the 20,000 tools required for ordnance production. Colonel Morrison's final inspection report documented quality levels that exceeded traditional hand-built machinery through systematic precision that eliminated individual variations. The modular machines demonstrated superior reliability under sustained loads because standardized components incorporated design margins based on statistical analysis rather than individual craftsman judgment. Spindle run-out accuracy averaged better than European standards, with 95% of production achieving tolerances within 5/10,000ths of an inch compared to traditional methods that accepted variations up to 15/10,000ths as normal craftsmanship limits. Heinrich Zimmermann's return visit in late 1942 revealed a transformed understanding of manufacturing philosophy that acknowledged American innovations while maintaining respect for European traditions. The German engineer observed modular assembly operations with the careful attention of a scientist studying successful adaptation, noting that Cincinnati's systematic approach had achieved through engineering analysis what European methods accomplished through individual experience. The Americans had essentially codified the master craftsman's intuitive adjustments into standardized procedures that any trained worker could execute with consistent results. William Crawford found his role evolving from skeptical traditionalist to quality mentor, who helped younger workers understand the mechanical principles underlying their systematic assembly procedures. His experience proved invaluable for training programs that combined modular efficiency with craftsman insight, teaching workers to recognize the subtle indicators of mechanical problems that systematic procedures might miss. The assembly line had not eliminated craftsmanship, but redistributed it from individual machine construction to systematic quality assurance that benefited entire production runs. Rose McCarthy's advancement to assembly line supervisor demonstrated how the modular system created opportunities for worker development the traditional apprenticeship methods had never provided. Her spatial intelligence and systematic approach to precision work made her ideal for training new workers in the three-stage program that had evolved into a comprehensive manufacturing education system. By 1942, she supervised teams that included former farmers, displaced factory workers, and recent immigrants who achieved precision manufacturing skills through systematic training rather than decade-long apprenticeships. The modern irony that connected Geier's wartime innovation to contemporary manufacturing challenges became evident as computer-controlled machinery faced setup time problems that 1940s technology had already solved. CNC machines, despite superior precision capabilities, required hours or days of programming, tool setting, and calibration procedures before beginning production runs. Complex part programs demanded skilled programmers who understood both machining principles and computer languages, creating bottlenecks similar to the master craftsman limitations that had threatened wartime production. Modern setup procedures included workpiece coordinate establishment, cutting tool measurement and offset calculation, machining parameter optimization, and program verification through simulation software that consumed time without producing parts. Small batch production often proved more efficient on manual machines operated by skilled machinists who could complete simple jobs, while CNC systems remained in setup phases. The fundamental challenge remained identical to Geier's wartime problem: balancing precision requirements with production speed through systematic approaches that eliminated individual bottlenecks. The enduring lesson of Cincinnati Milling's wartime revolution transcended specific technological solutions to address manufacturing philosophy that remained relevant decades after the assembly line delivered its last machine tool. Geier's modular approach had demonstrated that systematic precision could exceed individual craftsmanship while achieving production rates that traditional methods could never match. The key insight involved recognizing that complex machinery consisted of standardized subsystems that could be optimized independently, then combined through precision-engineered interfaces that eliminated assembly variations. American ingenuity had won the Industrial War not through superior individual machines, but through superior manufacturing systems that delivered precision at unprecedented scales. The 17-minute machine tools that armed democracy represented more than wartime emergency measures. They embodied manufacturing principles that transformed precision production from craft tradition into systematic science. The victory belonged not to better technology, but to better methods that proved American innovation could exceed European tradition through engineering analysis rather than individual experience.